Today we are going to learn about confidence intervals for the mean of a population. Let me remind you that what we are doing is inference, meaning that from a sample we want to draw conclusions about a population parameter, and it's not probability, which was one of the previous topics. Let us consider the problem of estimating the mean weights of boys in the UK. Suppose that due to the large number of boys involved, the distribution of their weights is normal. And let's assume we know its standard deviation. In order to get some idea of the mean, we must take a sample and obtain either a point estimate or an interval estimate for the mean. So if we take a sample, let's say of size 5, and find that the mean of this sample is 63 kilograms, this is a point estimate for the mean weight of the boys. Does it mean that the mean weight will be exactly that value? Certainly not, since if we take another sample, we might find another number. It would be nice if we can find a statistic that can give us a point estimate that exactly reveals the true value of the parameter of the population. However, this estimate depends on the sample we pick. Different samples nearly always provide different estimates due to the sampling variability. In practice, you hardly ever select a sample that will provide you with an estimate exactly equal to the value of the population parameter. Therefore, the point estimate we obtain from a sample for the mean, for example, says nothing about how close our estimate might be to the true mean. This variability of estimates brings about the importance of indicating how accurately we are estimating the population parameter. So an alternative to reporting a single sensible value for the parameter being estimated is to calculate an entire interval of possible values, an interval estimate, or called also confidence interval. So a confidence interval estimator for a population parameter is a rule for determining an interval that is likely to include the parameter. The corresponding estimate, so if I apply the rule once, I get what is called a confidence interval. So here I run a simulation for the boys' weights. What did I know is that the mean of I didn't know the mean, so I know that the boys' weights are normally distributed, being quite a big population, with an unknown mean and a variance 10.9 squared. Therefore, I know that the weights lie on a distribution for which I don't know the mean. Not knowing the mean, but knowing the standard deviation, means that I know the shape of my distribution, but I don't know exactly where it is placed. So the mean can be anywhere here. I don't know yet. What can I do to have an estimate about the mean? A confidence interval is always calculated by first selecting a confidence level, which is a measure of the degree of reliability of the interval. I chose here a confidence level in my simulation of 95% for the true mean of the boys' weights. In my simulation, each of the horizontal lines, green or red, corresponds to one sample chosen. So I chose to generate 100 samples. Let's take my last sample generated to see what happens with it. In my last sample of size 5, the mean that I obtained from the sample was 66.3. under this assumption that the true mean is 66.3, I know that the sampling distribution of the means is normally distributed with a mean that I would estimate now to be 66.3 because that's what I have, and the standard deviation 10.9 squared over 5, because I took samples of size 5. So this is how my sampling distribution of the mean will look like. And if I want a 95% confidence interval, I will take the interval containing the middle 95% of the data here, and that will be my confidence interval, which I have different ways to calculate it, and my answer will be, I'm not going to focus on the calculations, from 56.7 to 75.9. So if you look at my first interval here, what I'm talking about is from about 56.7, somewhere here, to 75.9, about 76. So that's how these intervals are constructed. The big idea here is that if we take repeated samples from the population and use the mean of each sample every time to construct a 95% confidence interval, in the long run, about 95% of these intervals succeed to contain the mean mu of the population. Remember that we don't really know what the mean of the population is. So in the case of my simulation, where I generated 100 intervals, this one being one of them, I see how I have 1, 2, 3, 4, 5, 6 do not contain the real mean. So I remind you that I have a 95% confidence level. So I'd expect about 5 of them not to contain out of 100. So this simulation works pretty well. The model and properties of confidence intervals are easily understood by first focusing on simple, although rather unrealistic situation. So we are always in the situation where we consider the population distribution to be normal and the value of the population standard deviation sigma to be known. One common mistake the students make is that they forget that the mean of the sample lies on another distribution. So the variance is changed, is a smaller variance rather than the initial variance of the population that is generally given. So because I calculate the mean of the sample, the confidence interval will be on this distribution, the sampling distributions of the mean. In the case when the population is not normal, but n is large enough, and being the sample size, and bigger or equal than 30, then we can apply central limit theorem and conclude that the sampling distribution of the mean will still be normal, and we can use a confidence intervals in the same way. Let us try this question. Please pause and read the question. I'm extracting the important data. The weight of all K-12 boys in the UK follow a normal distribution with an unknown mean and the standard deviation 10.9. A sample of size 5 is taken and the mean of the sample is 66.3. Therefore, I know immediately that my sample will be on a normal distribution with the same unknown mean and the standard and the variance 10.9 squared over 5. I want a 95% confidence interval for the mean of the population, and the confidence interval will be related to my sample. So for my sample, the mean is 66.3. Therefore, I am under this distribution. And I need to find a 95% confidence interval. That's the interval I need to find. One way to do it is to move on the standardized normal distribution. z is 0, 1 squared, and I'm looking for the z-scores here. Because it's a 95% confidence interval, I will need to look for an z-score corresponding to an area of 97.5. I can see that the z-score corresponding to 97.5% is 1.960. Therefore, this will be 1.960, and this point here will be minus 1.960 due to the symmetries in the standardized normal distribution. It has a mean of 0. So now I need to move these values on my initial curve, and so I'll use the formula of moving from one curve to another. So z and x are related by z equals x minus mu over sigma. But don't forget that I have some notation. So sigma in my question is a standard deviation of the initial population. However, I need to move on this curve. Therefore, I'm going to use x bar, and I'm going to use sigma over square root of n, because this one is the standard deviation of my sampling distribution of the mean of the distribution where this parameter is, where this statistics is. So algebra tells me that z times sigma over square root of n equals x bar minus mu. So mu is x bar minus z sigma over square root of n. However, I have a positive and a negative z, so if I call z as being 1.960, I will have mu contained in between. So I will have mu contained in between x bar plus z sigma over square root of n and x bar minus z sigma over square root of n. And these are exactly these values here. So the left value will be x bar 66.3 minus 1.960 times 10.9 over square root of 5. And if I use my calculator, I get 56.7, exactly the number we got on the previous page. So this will be the left bound of the confidence interval. And if I replace in the second part, 66.3 plus 1.960 times 10.9 over square root of 5, then I will get 75.9, which is from the previous page, the second number. Therefore, my confidence interval will be a 95% confidence interval will be between 56.7 and 75.9. Would you expect a 99% confidence interval to be narrower or wider? Just pause a bit and think about it. Look at our diagram. A 99% confidence interval will be from here to here, so of course it will be wider. I'm not going to calculate a 99% confidence interval for the population mean. You can do it. Your z value will change, and as you have 99% of the data in the middle, you'll have 1% on both sides. Therefore, you are going to look for this area of being 99.5. And 99.5, it's here, so your z value will be 2.576 instead of being 1.960. Question D. 2 more samples, each of size 5 are taken. Their means are used to calculate two 95% confidence intervals for the population mean. Find the probability that neither of these intervals will contain the true value of the population mean. Well, if it's a 95% confidence interval, we expect that 95% of our generated confidence interval will contain the true mean. So we expect that 5% will not contain the true mean. And because I generate this twice, the required probability will be 0.05 squared. Because the probability that the first interval will not contain the true mean is that one, and that's the probability of the second interval not containing the true mean. And this question assesses your understanding that 95% of all generated confidence intervals contain the true mean and 5% will not contain the true mean. We completed the question, but some observations are required. As you see, the confidence interval is always centered by your mean of the sample. So the mean of the sample is exactly midpoint of this interval. Therefore, if I calculate, for example, here, midpoint 56.7 plus 75.9 over 2, I am sure I'm going to get 66.3 because 66.3 is the mean of my sample. Sometimes you are asked to find n given the length of the interval. That's a formula that is quite useful. It is not in your formula sheet. So that's a quite useful formula. And the length of the interval will be the difference between the upper bound and the lower bound of the interval. So it's 2z sigma over square root of n is the length of the confidence interval. So see how it depends on the z value. Yeah, depending on your confidence level. So z value depends on the confidence level, on the variance or the standard deviation of the population, and on the size of the sample. The length of the interval does not depend on the mean of your sample. So if you look at our simulation before, you will see that all the intervals that I got in the simulation for 100 have the same length.